Okay, this is exercise 1.5 and it's an introduction to limits. Now we have come across limits a little bit before when we were doing differentiation. A limit is just basically a number that you head towards but never actually get to, if you like. Our notation for limits is the limit as x tends towards a of f of x, some function, is equal to p. So this means that as x approaches a, the value of f of x approaches p, but it never actually gets there. Now an example is find the limit as x tends to 2 of this function here. All we have to do here is just sub in for 2. Okay, so that's just equal to 3 times 2 plus 2 over 2 plus 4. 6 and 2 is 8 over 6. Okay, and you leave it at that. The answer is 8 over 6. Now, if we have something like this, however, we have a bit of a problem. Okay, so let's look at this one here. You've got limit as x tends to 3 of this thing here. So let's stick in our 3 and see what happens. You've got a 3 squared minus 9 over 3 minus 3. So you get 9 minus 9 over 0. Now, as we've kind of come across this before as well, a denominator, or a zero denominator on a fraction evaluates to infinity, and that's not desirable, let's say, okay? We call it the indeterminate form. So if we end up with something like this, the way we solve it is, well, we have a couple of options. What we could do first is you could factorize the top. X plus 3, x minus 3, divided by x minus 3, and then these two things cancel, and you end up with x plus 3. And then you do the limit as x tends to 3 of x plus 3, which is a 6, okay? So that will work out okay as well. Now let's look at the limit of a function 1 over x as x tends towards infinity. Okay, so f of x is 1 over x. Sorry, pen gone again. Okay, so let's think about it. F of x is equal to 1 over x. So let's say f of 10 is 1/10. Now let's take a bigger number, 1,000,000. So what you're noticing here, hopefully, is that as the numbers on the denominator get bigger, the value of the fraction actually gets smaller, okay? So what we say is that the limit as x tends to infinity, so in other words, when the denominator is getting infinitely big, you have 1 over a huge, huge number, and it tends towards 0, okay? Similarly, regardless of what you have at the top of your fraction, you can say that the limit as x tends to infinity of any number k over x is also equal to 0. So if you have like 10 over some massive number, that's eventually also going to 0. So these two boxes are important. I'm just going to remember them when we're doing future sums. Okay, so how we're going to put this into operation is we're going to do some examples here. If we have this limit here, we want to evaluate the limit as x tends to infinity of 4x plus 1 over 2x plus 3. Now it doesn't make much sense to start sticking in infinity there because you've got infinity over infinity, which is a bit meaningless. So what how you're going to cater for this type of an arrangement is you're going to divide top and bottom, numerator and denominator, by the highest power of x. Now you can see you just got x to the power of 1 all the same, all through here. So what we're going to do here is divide above and below by x. So what we say is the limit as x tends to infinity of 4x plus 1 over 2x plus 3 is the same as the limit as x tends to infinity. And we're going to divide by x. So if I divide 4x by x, you get 4. If I divide 1 by x, I get 1 over x. If I divide 2x by x, you just get a 2. And then if you divide 3 by x, you get 3 over x. Now, we've said already that as x tends to infinity, that becomes 0, and this becomes 0. So you just end up simply with 4 plus 0 over 2 plus 0. 3 over infinity is still basically 0. So you end up with 4 over 2, which is a 2. Something similar here, except this time we want the limit as x tends to infinity of this expression here. You have nx squared, so we're going to divide above and below by this x squared this time. So what we say is limit as x tends to infinity of 3x squared minus 2x plus 4 over 5x squared plus 4x minus 3 is equal to, now divide that by x squared, I get a 3. I divide 2x by x squared as well. I divide 4 by x squared, which will give me 4 over x squared. Divide this by x squared, you get a 5 minus 4x over x squared minus 3 x squared. Then you get, that's equal to, sorry, I need a limit sign here. That's equal to limit as x tends to infinity of 3 minus, okay, so one of the x's cancel, you get 2 over x when you divide 2 over x plus 4 over x squared, divide that by 5 minus 4 over x, so x divided by x squared is 1 over x or whatever, minus 3 over x squared. Now, when x tends to infinity, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. So what you have is 3 minus 0 plus 0 over 5 minus 0 minus 0, and that's equal to 3 over 5. That's your answer there. Okay, moving along, we're just looking at what we call continuous and discontinuous functions. Now, continuous function is one that you can put your pen on the page and you can draw it, and you don't have to take your pen up at all until you get to the end of the function. That's what we call a continuous function. And again, if you want to put it in more complex maths language, you can say that as x tends to some value a, it's continuous. We say that a function is continuous at x equals a if the limit when x is going towards a of f of x is equal to simply f of a. That's sort of very complex language for meaning there's no gaps or breaks as you draw the function. These below are discontinuous functions. This one has a discontinuity at x equals minus 1. This has a discontinuity at x equals plus 1. Just to note here that, you see that dashed line there? That's what we call an asymptote, and it's a line towards which the function tends but never actually gets there. And you'll get asymptotes when you're graphing a function which looks like 1, for instance, 1 over x plus some other number. Okay, then you'll get this sort of a strange shaped graph. So that's discontinuous, and you'll notice that for a discontinuous function you have to take your pen up off the paper in order to draw the full function. It's disjointed, so here you take your pen up and there. These are discontinuous. Okay, what I want you to look at is exercise 1.5 on page 28 of book 7. If you do questions 1, 3, 5, 7 and 9, that should cover you, and I'll put up solutions for those on Schoology. Okay, thank you.